Hello students, this is Dr. Anita Raj welcoming you for an important session in haloalkanes and arenes. In this session, we shall see the general methods of preparation of haloalkanes in which you can expect definite questions in board exams. So let us move into the topic students, the methods of preparation of haloalkanes. Okay. See from alkanes, how these haloalkanes are prepared from alkanes. That's the first methodology. Actually, alkanes on direct halogenation in the presence of sunlight gives haloalkane. Okay. So actually this will be following, that is the preparation from alkanes, and that too in the presence of sunlight will be following based on free radical mechanism. Okay. Okay. All halogenation processes of alkanes are exothermic process. What do you mean by exothermic? Energy will, like heat energy will be dissipated out. Okay. But in the case of iodination alone, it is little unique and it is endothermic in nature. Okay. So let us move to the first methodology under alkanes. The first one is chlorination. How chlorination is done? See, actually chlorination of methane in the presence of sunlight or heat gives a mixture of products. Okay. Mean we'll be getting different types of or different types of products, and that's why it's given as mixture of products. Let us see what are the products obtained. See here methane CH4 in the presence of chlorine, either in the presence of sunlight, that's why it's given as H nu, or at high temperature, that is 520 to 670 Kelvin, it's possible to produce the haloalkane. Let us see what are the different types of haloalkanes produced here. See here CH3, Cl, okay, methyl chloride, and also it's possible to produce CH2, Cl2, okay, CH2, Cl2, and then CHCl3, that is chloroform, okay, and then carbon tetrachloride. So all these different types of products are produced, so that's why it's given as mixture of products. But if you want a single product, then the proper ratio of this proper ratio of halogen and alkane is used. If proper proportion of this halogen and alkane is used, then it is possible to get monohalogen compounds. Monohalogen means this is a monohalogen. Only one halogen is there. But whereas here 2, here 3, here 4, is it not? So if it is needed to prepare monohalogen compound, then proper ratio of this halogen and alkane should be used. Understood, students? In the case of higher alkanes, see this is a lower alkane, methane is a lower alkane. But in the case of higher alkane, see here it is a higher alkane having 3 carbons, is it not? In the case of higher alkanes, a mixture of primary, secondary and tertiary haloalkanes are obtained. Understood? So when you are making use of higher alkanes, it is possible to produce what to say, primary, secondary and tertiary haloalkanes. Okay. Let us see the products now. So in the presence of what is this? Chlorine and sunlight, it's possible to produce a mixture of product, that is CH3, CH2, CH2, Cl, okay, plus a secondary product CH3, CH, Cl, CH3. Okay. So this is, what is this? Methane, ethane, propane. You know? So propyl chloride or chloropropane. Okay. Chloro 1, chloropropane. Okay, 1 chloropropane. Why 1 chloropropane? Because the chlorine atom is attached to the first carbon atom. That's why it's 1 chloropropane. See, already I have dealt with the IUPAC naming of these haloalkanes in my previous videos. So I shall give the link of that particular video so that you can have a clear-cut idea on the IUPAC naming of haloalkane. So I'll be giving the link in my description box. Understood? So this is isopropyl chloride. Okay. So this is isopropyl chloride or 2-chloro. If you want to write the IUPAC name, it is 2-chloropropane. Okay. It is 2-chloropropane. So here it's possible to get 45%, whereas here it's possible to get 55%. So this is the major product. Understood, students? Next methodology is fluorination. Okay, so we are seeing the halogenation of alkanes. So how fluorination is taking place? Actually, this fluorination of alkanes takes place with an explosive violence. Okay, so it takes place with an explosive violence. Along with this, you'll be getting the product. So alkyl fluorides are prepared by indirect method. So we are not making use of, just like that of chlorination. See, in chlorination we are adding chlorine directly, is it not? But here in the case of fluorination, we are not adding fluorine directly. Instead, we are making use of an indirect method. Okay, we are using mercurous fluoride. Okay, so this is mercurous fluoride, mercurous fluoride, So mercurous fluoride, when it is treated with chloroethane, see CH3, CH2Cl. This is chloroethane. What happens is that substitution takes place. Okay. See here, instead of chlorine, fluorine will be added. Okay. So we will be getting fluoroethane means CH3, CH2, F. Okay. Plus, see here what's happening here. See this fluorine. One of the fluorine is added here. Okay. Since it is two molecules, two fluorine atoms, and this chlorine will be coming and added up to this one. So you'll be getting the product here 2CH3 CH2F plus Hg2 CH2. Okay, so mercurous chloride. So this is the product. This is how this fluorination is taking place in the case of alkanes. And next comes iodination. Iodination can be done by heating alkane with hydroiodic acid or nitric acid, which oxidizes Hi to I2, thereby preventing backward reaction. Okay, thereby preventing this backward reaction. So let us see what is happening here. See, when methane is treated with iodine in the presence of heat energy, it will be producing CH3I, okay, methyl iodide plus Hi. Okay, and now if in the presence of, see, this reaction takes place in the presence of heat energy, but now when methane is treated with iodine in the presence of nitric acid, what type of reaction takes place? Let us see. It is CH3, again methyl iodide, we are getting a haloalkane, okay, plus Hi. Okay, now what happens? Why we are making use of this nitric acid? The reason is the Hi which is produced here will be reacting with the nitric acid, and it forms iodine again. Okay, so let us see how this nitric acid gets split up. HNO3, this NO3 is getting split up into NO2 and oxygen. Okay, now what happens is this iodine, it combines. Okay, since here we are having two molecules, this will be getting converted to iodine I2 plus NO2. Okay, so NO2, this NO2 to NO2 plus this oxygen will be reacting with this hydrogen, and it forms water molecule. Okay, it forms water molecule. So this is what happening in the case of this when you are adding nitric acid. Okay, so during iodination can be done by heating alkane with hydroiodic acid or nitric acid. Here I have used nitric acid, which oxidizes this Hi to iodine. Okay, so this iodine is produced by the reaction with Hi with nitric acid. So when during this reaction, iodine will be produced, and this iodine will be reacting with methane to form ethyl iodide. So that way we can prevent the backward reaction. Okay. So next important methodology is from alkenes, students. So addition of HCl, HBr, Hi to alkenes gives haloalkanes, and it can be done through Markovnikov's rule or anti-Markovnikov's rule. Okay. So what does Markovnikov rule? See, actually as per Markovnikov's rule, when we are adding a halogen or hydrogen halide to a double bonded compound, what happens is the hydrogen will, based on Markovnikov's rule, hydrogen will be getting added up to a carbon atom which is having the highest number of hydrogen atom. See here, near to this double bond we are having two carbon atoms, is it not? So when you are adding a what is hydrogen halide, the hydrogen will be getting added up to the carbon which is having higher number of hydrogen atoms. Okay, so this is based on Markovnikov's rule. Now again let me explain how this reaction takes place. I have taken propene CH3 CH double bond CH2 plus HBr. See, in the absence of an organic peroxide, see, for three types of reactions I have taken. One is HBr in the absence of hydrogen peroxide. So that in the absence of peroxide, this reaction takes place by Markovnikov's rule. What is the product, students? CH3 single bond CH. Now again CH. So this hydrogen will be getting added up to this carbon, so this becomes CH3, is it not? So CH3, and what happens to this Br? It will be getting added up to the next carbon which is having the lowest number of hydrogen atoms, is it not? So here becomes CH, so this is the product. Okay, this is based on Markovnikov's rule. And next is, since because we are not using peroxide, it is taking place by Markovnikov's rule. The next methodology is in the presence of peroxide. In the presence of peroxide, if this reaction takes place on the basis of anti-Markovnikov's rule. What is anti-Markovnikov's rule? The hydrogen will be getting added up to the carbon which is having the least number of hydrogen atom. Is it not? To the carbon which is having the least number of hydrogen atom. So what happens? What could be the product now? Let me tell me students, CH3. This CH becomes CH2 because the hydrogen is getting added up to that carbon atom, and next CH2Br. Is it not? So the Br will be getting, based on anti-Marconi constant, the Br will be getting added up to this carbon. Understood students? And see here, this reaction actually, this the first one that is based on Marconi-Krebs rule, this is an electrophilic reaction. Okay, electrophilic addition. Okay. Whereas in the case of the next one, in the presence of peroxide, this reaction is taking place based on anti-Marconi-Krebs rule, and this will be following a free radical mechanism. I have written the product directly, but actually this will be following a free radical mechanism, and this is called peroxide effect. This reaction is called as peroxide effect. Okay, peroxide peroxide effect, or another name is also there, that is Karash, K-A-R-S-C-H, Karash effect. Okay, so either peroxide effect or Karash effect, this reaction is called. Okay, now see here students, this peroxide effect or Karash effect is applicable only for HBr. Okay, and it is not applicable for the rest of the hydrohalides. Okay, mean if you are making use of HCl, though in the peroxide it is not possible to expect this type of anti-Marconi-Krebs rule of addition, that is Karash effect. Rather it will be following the previous one, that is Marconi-Krebs rule addition. Okay, so only HBr in the presence of peroxide will be exhibiting this peroxide effect or Karash effect, but the other halides, hydrogen halides will be following the Marconi-Krebs rule or not the Karash effect. Okay, so what could be the product students? CH3, CH, Cl. Okay, Cl, CH3. So this is the product. Understood students? The reason why we are expecting why it's not following this Karash rule is because this HCl bond. Okay, the HCl bond is polar and can undergo homolytic fission even in the presence of peroxide. Okay, it will be undergoing homolytic fission even in the presence of peroxide. That's why it's not undergoing the Karash effect or the peroxide effect. Understood students? Next is from alcohols. Okay, so from alcohols by the reaction with phosphorus halides. Okay, from alcohols how this reaction is taking place. So that is in the presence of phosphorus halides. I have taken two types of phosphorus halides, phosphorus pentachloride and phosphorus trichloride. So let us see how this reaction takes place in the presence of phosphorus pentachloride. See here, this I have taken an ethanol, that CH3CH2OH. Now let me, for you to understand easily and for you to understand and learn easily, I am splitting this PCl5 to PCl3 Cl Cl. Okay, now see how the product is formed. Okay, see here, this oxygen will be getting split like this. Okay, so this O will be getting added up to this PCl3. Okay, and this Cl will be getting added up to this H. Okay, and this Cl will be getting added up to this CH3 CH2. Okay, now can you tell me the product students? See here, Cl is getting added up to this one, is it not? So the product will be CH3 CH2 Cl plus, what's the next product students? This O is getting added up to this PCl3, is it not? So POCl3. Okay, POCl3 plus next this Cl is getting added up, this Cl is getting added up to this hydrogen, is it not? So HCl. Okay, so we are getting, what is this? Chloroethane. Is it not? Haloalkane is chloroethane. This is chloroethane. Okay, next we shall see the next product. See here, I have taken isopropyl alcohol, CH3 CHOH CH3, isopropyl alcohol and PCl3. See, let us see how this PCl3 is getting splitted up. See here, PCl3 gets splitted up like this. Okay, and now what happens is this OH. Okay, we are having three molecules. Is it not? We are having three molecules. So this 3 OH, we are having 3 OH then. So this 3 OH will be getting added up to this phosphorus and we'll be having H3PO3. This is the byproduct, H3PO3 plus, what is the rest of the product? this 3 chlorine will be getting added up to this CH. Okay, so this product will be CH3, CH, Cl, CH3. Okay, 3 times. Okay, now we have got a product. Now next is from alcohol using phosphorus and iodine. Okay, how haloalkanes are prepared from alcohol using phosphorus and iodine. See, actually this is prepared by treating alcohol with red phosphorus and bromine or iodine. Okay, so either this phosphorus will be treated with bromine or phosphorus with iodine in the presence of alcohol. It's possible to produce haloalkanes. Okay, so let us see how this reaction is taking place. Actually, this phosphorus is treated with bromine. So first we'll be getting PBr3. Okay, PBr3 4 times. Now this PBr3 will be treated, we will be reacting with ethanol, CH3, CH2, OH. I have taken 3 molecules. So now what happens, how this reaction takes place, let us see. See, this is getting splitted like this, okay. And now this Br, okay, this also gets splitted, right. So this Br3 Br molecules will be getting added up here, whereas this OH will be 3 OH molecules will be getting added up to this one. So what is the product, students? CH3, CH2, Br, okay, 3 molecules plus H3, PO3, okay, H3PO3. So this is bromoethane, okay, this is bromoethane. So same methodology is taking place here again in the presence of iodine. When phosphorus is treated with ethanol in the presence of iodine, this reaction takes place. So let me write the product now. 4PI3. Okay. Now this PI3 will be reacting with this. Okay. So PI3 will be reacting with this. So the same type of reaction mechanism takes place. It gets splitted here. So this I3 will be getting added up here, okay, and this OH will be getting added up to this phosphorus. So 3 CH3 CH2 I plus H3 PO3. Understood, students, how the product is formed? So this is iodoethane. So iodoethane is produced, okay. And the next important methodology is by the action of thionyl chloride, okay. What is thionyl chloride? SOCl2. SOCl2 is thionyl chloride. So how this haloalkanes are produced by thionyl chloride? Chloroalkanes can be prepared by refluxing alcohols with thionyl chloride in the presence of pyridine. Okay, so this is alcohol ethanol I have taken, and this is thionyl chloride in the presence of pyridine. So how this reaction takes place? For you to learn easily, I am splitting this. Okay, then again here also splitting takes place. Okay, and this SOCl2 will be getting splitted to ESO, Cl, Cl. Okay. Now what happens? See, this oxygen will be getting added up to this SO. Okay. And one of the chlorine will be getting added up to this one. Okay. And this hydrogen gets added up to this Cl. So come on, students, tell me the product now. See here, CH3, CH2, and this chlorine is getting added up. Is it not? So the product will be CH3, CH2, Cl plus what's the next product? Yes, so this oxygen is getting added up to SO, is it not? So SO2 sulfur dioxide plus HCl, is it not? So this is the product. So what is the name of this compound, student? This is chloroethane, is it not? This is chloroethane. The reasoning of question, why is thionyl chloride is the best reagent for converting the alcohol to chloride? The reason is the byproducts formed are gaseous in nature. That's why it will be escaping, so you'll be getting the product alone. Whereas in the other cases here we are having H3PO3, and in the treatment with PCl5, PCl3 also we are getting H3PO3. So that has to be precipitated and removed, is it not? Whereas here this is not the case. That's why it's considered to be the best reagent. Understood, students? Next methodology is by halide exchange method. Okay, so halide exchange method. See, under halide is this method we are having two types. Okay, Finkelstein reaction and Schwartz reaction. Okay, Schwartz reaction and Finkelstein's reaction, both naming reactions. Actually, this is used to prepare iodoalkanes which are difficult to prepare by direct iodination of alkanes. Okay, So used to prepare iodalkanes which are difficult to prepare by the direct iodination of alkanes, and also in this method exchange of halides to iodide takes place by heating haloalkanes with NaI in the presence of acetone. Okay, so it's just a exchange reaction. See here it's a haloalkane, it's already a haloalkane, okay, alkane. So that's why we are using sodium iodide, that too in the presence of acetone, and at high we should heat it. When this haloalkane is heated in the presence of sodium iodide and acetone, we will be getting the product RCH2I. Okay, so just the exchange, okay, just an exchange, okay, plus NaCl. Okay, here also the same thing happens, just an exchange. Okay, so RCH2I, okay, RCH2I plus NaBr. For what purpose we are using this acetone? For what purpose we are using this acetone? Actually, the role of acetone is, see here we are getting the products NaCl and NaBr. Okay, so and these are less soluble. Actually, these are less soluble in acetone. Normally, if it is in the presence of water, it will be dissolving easily, is it not? But in the case of acetone, they are less soluble. Since they are less soluble, this can be easily precipitated. These two byproducts can be easily precipitated. That's why, and it can be removed easily. So we can prevent the back reaction. So in order to prevent the back reaction, we are using acetones. Understood, students? And the next methodology is Schwartz reaction. Actually, here also the same thing happens. Exchange of chlorine, bromine or iodine to fluoride by heating with AgF or H2F2 or COF2 or SbF3. Okay, so either by treating with AgF or H2F2 or COF2 or SbF3, it is possible to exchange the halogen. Okay, this X represents nothing but chlorine or bromine or iodine. So when it is treated with silver fluoride, just the exchange of the halogen takes place, and what happens here, just the exchange. Okay, so here it's an exchange. Okay, students, so CH3 CH2F plus AgX. Okay, where this X is nothing but these things. Okay, chlorine, bromine, iodine. Understood, students? The last methodology is Hunziker's reaction. That is from silver salt of fatty acids. Okay, so when a silver salt of fatty acid is heated with bromine in CCl4, a bromoalkane containing one atom less than the fatty acid is obtained. Okay, so when this silver salt of fatty acid is treated with carbon tetrachloride in the presence of bromine, it is, and when it is heated, we will be getting the haloalkane, one, that to one atom less than that of this fatty acid. Let us see how this happens. Okay, so here this is silver butanoate. Okay, silver butanoate, and now when it is treated, see this bromine, it gets splitted like this, Br. Okay, and now this also gets splitted like this. Okay, so what happens? This COO will be getting converted, like it will be liberated as carbon dioxide, CO2, and now one Br will be getting added up to this, so AgBr. Okay, AgBr, and another Br will be getting added up to this one, so CH3, CH2, CH2, Br. Understood, students? See here, see this compound. This compound is having one carbon atom lesser than this one. See here 1, 2, 3, 4. Whereas here 1, 2, 3. Okay, because this carbon COO gets escaped as carbon dioxide as a gas, and this silver bromide, it gets precipitated. So that's, it's possible to produce haloalkane from the silver salt of fatty acid by Hunziker's reaction. Understood, students? Well, fine students, you might have understood what I have taught today. Let me meet with another important topic in my next video. Until then, it's Dr. Anita signing off from you. Thanks for watching.